Today we shall be considering the topic Introduction to Electromagnetic Waves. And we're going to start with the simple question. The first question is, what is electromagnetism? What is electromagnetism? Electromagnetism is a branch of physics that deals with the study of electromagnetic forces. The branch of physics that deals with the study of electromagnetic forces. We can as well define it as the branch of physics that deals with the interaction between electrically charged particles and associated fields. The next question is, how does electromagnetic radiation occur? How does electromagnetic radiation occur? Electromagnetic radiation occurs when atomic particles like electrons are accelerated by electric and magnetic fields. Electromagnetic radiations occur when atomic particles like electrons are accelerated by electric and magnetic fields. We are going to say briefly about electromagnetic waves. Electromagnetic waves are those waves which are created as a result of vibrations between electric and magnetic fields. So they are those waves that are created as a result of vibrations between electric and magnetic field. One special attribute about electromagnetic waves is that they travel at the speed of light. So whether it is gamma ray or X-ray or UV ray as the case may be, or even radio wave, they all attain the same speed, which is the speed of light. We are going to be looking at Maxwell's equation. Here we have that Maxwell's equations are the four fundamental laws that govern electromagnetic phenomena. They include Gauss' law of electricity, Gauss' law of magnetism, Faraday's law, and the ampere Maxwell's equation. Okay, so the table below will give a better explanation to what we have listed. So we have the Gauss law of electricity as number 1, Gauss law of magnetism as number 2, the Faraday's law of induction, and then the ampere Maxwell's equation. The definitions are stated as follows. So you now see the mathematical expression representing the definition. You can see, so you see where the equation is written and then the definition as well. Okay, so the Gauss law of electricity states that the net flux of electric field in a closed surface is directly proportional to the enclosed electric charge. The net flux of an electric field in a closed surface is directly proportional to the enclosed electric charge. So you can see the mathematical expression here. So E here represents the electric field in consideration, and this is the area being considered in the closed surface, and this is directly proportional to the charge in that surface. So we have that the net flux of an electric field in a closed surface is directly proportional to the enclosed electric charge. So the constant here, epsilon naught, this one is a constant. Okay, let's go down to Gauss' law of magnetism. The law states that no magnetic monopole exists and that the total flux through a closed surface must be zero. No magnetic monopoles exist, and the total flux through a closed surface is zero. You can see the statement being explained by the equation here. So you can see the surface integral of the field, which is a product of the area in consideration, and then this will have equals to zero. Okay, so I read further. This means that the number of magnetic field lines that enter and exit through this closed surface is the same. This is explained by the concept of magnets that has a north and south pole, where the strength of the north pole is equal to the strength of the south pole. But I want us to note the mathematical expressions for Gauss' law of electricity and Gauss' law of magnetism, and then the Faraday's law of induction and the ampere Maxwell's equations. The Faraday's law of induction states that the magnitude of the EMF induced in a circuit is proportional to the rate of change of time of the magnetic flux that cuts across the circuit. So you see the mathematical expression for that statement. We now move to the ampere Maxwell's equation. So the law shows the relationship between the flow of current and the magnetic field around it. Suppose a wire carries a current I. The current produces a magnetic field that surrounds the wire. So the ampere Maxwell's equation here comes with the flow of current, and then you see the magnetic field, the mathematical expression for magnetic field, and the symbol for current. So the law shows that the relationship between the flow of electric current and magnetic field around it. Suppose the wire carries a current. The current produces a magnetic field that surrounds the wire. So the expression is as follows. Let's look at this question. The basic principles of electromagnetism can be expressed in terms of four equations called what? We have already explained that, so the answer is the Maxwell's equation. The basic principles of electromagnetism can be expressed in terms of four equations, and what are they? Alright, let's move forward. What does Maxwell's equation explain? What does Maxwell's equation explain? Maxwell's equation explains how electric charges and magnetic currents produce magnetic and electric field. They explain how electric charges and magnetic currents produce magnetic and electric field. So the Maxwell's equation also describes how electric field can create a magnetic field, or how magnetic fields can create electric field. We can as well say that the Maxwell's equation describes how electric and magnetic fields are being created and vice versa. The next one here says the Maxwell's equation predicts that the changing magnetic field produces an electric field, while the changing electric field produces magnetic field. Please, you're watching Supreme Online Lectures. I would like you to encourage us. If you are watching on YouTube, this is the link for YouTube Supreme Online Lectures. Please endeavor to subscribe to our channel as well. If you are watching on Facebook, it's still the same link the same name, please do us a favor by following our page. I would really appreciate. Let's look at this question. This question says, what is electromagnetic spectrum? Before we answer that question, I would like to introduce a particular figure. So this figure will give us a clearer picture of what the electromagnetic spectrum is all about. In this figure, looking at it critically, you see the electromagnetic waves. So here you can see that order of arrangement. This is the gamma ray. Let me change this color. I think I would prefer the red color. Okay, so we have the gamma ray, the X-ray, the ultraviolet ray, the visible light, the infrared ray, the microwaves, and the radio wave. Looking at this figure, up here you see the frequency is measured in hertz, the unit of frequency, and here you have the wavelength in meters. So you can see that while the wavelength is increasing from here, so as you're going down, the wavelength is increasing, the frequency is decreasing. Okay, so this means that frequency is inversely proportional to wavelength. The question was, what is electromagnetic spectrum? You can see that this order of arrangement of electromagnetic waves in their wavelength and frequency is simply referred to as the electromagnetic spectrum. You now see the gamma ray, the X-ray, the ultraviolet ray, the UV ray, visible light, infrared, microwaves, and the radio waves. Let's go to the definition now. Electromagnetic spectrum is the range of all possible frequencies and wavelengths of electromagnetic radiation. Electromagnetic spectrum is the range of all possible frequencies and wavelengths of electromagnetic radiation. So you can see that table, that figure, is a range that comes with all possible wavelengths and frequency of electromagnetic radiation. That order of arrangement of all possible wavelengths and frequencies of the EM radiations is referred to as the electromagnetic spectrum. You can as well say that the range of wavelength or frequency over which electromagnetic radiations extend. So it is the range of wavelength or frequency over which electromagnetic radiation extends. If you come back to this figure, I made mention about the frequency and the wavelength. And I also said that frequency is inversely proportional to wavelength. You can see that if I begin to list the members of this electromagnetic spectrum in order of increasing wavelength, since we have a short wavelength up here, here we have short wavelength. Take time to write this. Short wavelength. Here we have long wavelength. Alright, so electromagnetic radiations that have shorter wavelength have a higher penetrating power than the ones that have a longer wavelength. So looking at this, you see that gamma ray has a higher penetrating power than X-ray. X-ray can as well penetrate because it has a short wavelength, but the wavelength of X-ray compared to gamma ray is longer. So if you're comparing X-ray, the wavelength of X-ray and that of the UV ray, the ultraviolet ray, which one is longer? You see that the UV ray has a longer wavelength. If you now compare the wavelength of the UV ray with that of visible light, the visible light has a longer wavelength to that of the UV ray. If you're comparing the wavelength of the visible light to that of infrared, infrared also has a longer wavelength. So that's how it operates. So those we have the gamma ray, it has a short wavelength, and then followed by X-ray, followed by UV ray. So as it is coming down, the wavelength is increasing. While the wavelength, here we have short wavelength, long wavelength. On the other hand, if we are talking about frequency, frequency here is longer frequency. Remember that V equals to F lambda. Okay, so if we are solving for F, you can see that frequency is inversely proportional to wavelength and vice versa. So when we are talking about a short wavelength, indirectly we are referring to long frequency. Here we have a long wavelength, so indirectly we are referring to a short frequency. So if you are asked to list members of the electromagnetic spectrum in order of increasing frequency, you have to start where you have a short frequency and then begin to list them. Okay, so listing the members of electromagnetic spectrum in order of increasing frequency. Here we have a short frequency, we have long frequency. So we'll start from the radio wave and then the microwave, infrared, visible light, UV ray, X-ray, and gamma ray. If we are to list the members of the electromagnetic spectrum in order of decreasing wavelength, you now see we have a long wavelength here and a short wavelength here. It's still the same thing as we are listing members of the electromagnetic spectrum in order of increasing frequency. So if I say decreasing wavelength, then you now see we move from the longer wavelength to shorter wavelength. So it's still the same thing as the first question. Please note it. Now, if you are asked to list members of the electromagnetic spectrum in order of, let me check well, in order of increasing wavelength, then we have short here, long wavelength, so we'll come down. That order is order of increasing wavelength. So you start from where you have a short wavelength, which is gamma ray, X-ray, UV ray, visible light, infrared ray, microwave, radio waves, and all of that. In the same way, if you are asked to list members of the electromagnetic spectrum in order of decreasing frequency. Look at this, we have long frequency here. Here we have short frequency. So decreasing frequency, then we'll move from long to short. Okay, so by the time I get there, you will really understand what I'm trying to say. Let's check few questions. This one says, electromagnetic spectrum is made up of two broad components. Name them. What are the components of electromagnetic spectrum? We have the long wavelength and the short wavelength. So those are the components, the long wavelength and the short wavelength. So the electromagnetic spectrum is subdivided into two. The region where we have a short wavelength, at that point, the members of the spectrum have a higher penetrating power, and the side of the long wavelength here, they have a lower penetrating power as well. So here we have short wavelength, and here we have long wavelength. So here you will see the infrared, microwave, radio wave, visible light. For those ones that are short, you see gamma ray, X-ray, and UV ray. Let's look at the next question. Name the components. We have already named the components and parts in each component in order of increasing frequency. Okay, so the question, you have to first of all think of it. What are the components, the long wavelength and the short wavelength, and the parts in each component? Now, there is a clause here, in order of increasing frequency. In order of increasing frequency. So you don't have to name the members of the electromagnetic spectrum carelessly. You have to name them in order of increasing frequency. So you can see here that we have short frequency here, and long frequency. So if we are listing them, we'll start from the lowest here. So for the components, we'll start for the first component. We'll start from radio wave, microwave, and infrared. And then for the short wave, we'll mention UV ray, X-ray, and gamma ray. So for the long wave, we'll mention radio wave, microwave, and infrared and visible light. Alright, so let's go back to the solution. Long wave. So for the first component, long wavelength, we have radio wave, microwave, infrared. And for those ones that are short, you have visible light, UV ray, X-ray, and then the gamma ray. Okay. This other one says, what would the equivalent in order of decreasing wavelength be? What would the equivalent in order of decreasing wavelength be? If you are listing the members of the electromagnetic spectrum in order of decreasing wavelength, I would like you to think, because I've already explained this. Okay, so if you are considering the components in terms of short wave and long wave, and you want to list them in order of decreasing wavelength, where would you start from? Think about it. Write down your answer. Then you compare with what we have if it is the same. Alright, so this is my answer. For long wavelength, we would have radio wave, microwave, and the infrared. And for short wavelength, have visible light, UV ray, X-ray, and gamma ray. Okay. The next question here says, briefly explain why a car parking under the sun is hotter than the ambient temperature. If you go to a place and park your car, attain a function, and the next moment you come back to that vehicle to start it or to just open the door, you will see that the temperature of that vehicle will be higher than the ambient temperature. What could be the reason? What could be the leading cause of this? Okay, let's look at it. The solution. So the glasses of the vehicle behave like a greenhouse. It is transparent to solar radiation and opaque to infrared radiation. Shorter wavelength has ability to penetrate objects. So the radiation that comes from the sun, solar radiation, usually has, it's the UV spectrum. How do I put it? Is the UV section of the electromagnetic spectrum. So you see that it has the ability to penetrate through the glass. When it re-radiates in the seat of the vehicle, inside the vehicle, it re-radiates, it becomes infrared. So infrared would tend to be opaque to the windscreen, but it is transparent to UV ray. So let's read this again. It is transparent, or let me take it again. The glasses of the vehicle behave like a greenhouse. It is transparent to solar radiation and opaque to infrared radiation. The blocked infrared is partly radiated out, while part is re-radiated back into the vehicle, causing more heating effect than it would be without glasses. Okay, so it is just as simple as that. The energy from the sun comes in the form of the UV ray, and the UV ray has a shorter wavelength, so it will penetrate the glasses of that vehicle. When it re-radiates, it becomes heat, infrared, heat waves. When it re-radiates in the form of heat, it does not have that same amount of energy for it to escape through the glass, but rather it becomes opaque to those windscreens and to the windscreen, and as such would not be able to escape through the windscreen. So very little of it would escape, and the other part of it will still come back to the vehicle. The process continues like that, such that you see an increase in the temperature of that very vehicle. We have talked about the members of the electromagnetic spectrum, starting from the gamma ray, the X-ray, the UV ray, visible light, infrared, microwave, and the radio wave. We are still going to throw more light on those members of the electromagnetic spectrum one after the other. We are starting with the first one, the gamma ray. Looking at this figure, you see a man lying down, and you see that radiation is being focused on his body. Okay. That radiation is the gamma ray. If you look critically and carefully, if you look into this figure, you will see a root. Okay, so the gamma ray can be used for treatment medically. Could be used to kill cancer or cancerous cells in the body. If you look at the second figure here, you see alpha particles. These ones can be terminated either by the human hand. Beta particles can penetrate but can't penetrate aluminum metal. Okay, here we have the gamma ray. So gamma ray has a short wavelength, a higher penetrating power. It has the potential to penetrate the human skin and even the aluminum metal. It could be absorbed by heavy metals like lead and all of that. Okay, let's go to proper explanation. Gamma ray extends from 0.01 nanometer to less than 10 to the power minus 5 nanometer. When they say nanometer, what do we mean? 10 to the power minus 12. Oh, sorry, minus 9. Extends from 0.01 times 10 to the power minus 9 meters to less than 10 to the power minus 5 times 10 to the power minus 9 meters. Are you with me? Okay, I move further. They are produced by radioactive decay. They are produced by radioactive nuclei and during certain nuclear reactions. So all the members of the electromagnetic spectrum has different ways that we can produce them. We are going to address them one after the other. But in the case of gamma ray, they can be produced by radioactive decay of the nuclei of an atom. Gamma ray can damage the living tissues and have highly penetrating power. So those of us who are in the medical field, you have to know about the hazards of this radiation. For the radiographer that is working with all these radiations, or even those of us who stay in the lab, you don't enter the lab carelessly. You may not feel this radiation that they are eating up things in your body because it does not have any heating effect, but they are dangerous to the human body. So gamma ray can damage living tissues and have highly penetrating power. They are used in medicine to destroy cancerous cells. So gamma ray has an application in medicine and could be used to destroy cancerous cells. The X-ray. We look at this, you see the radiographer trying to study the human bone. This picture is gotten from the picture of X-ray. So you see the human hand, the femur, or in fact the body of human being. So to that X-ray, the skin is transparent to the human skin. You can't see the skin at all. It's just detecting the skeleton. Look at this other one. This person has a broken bone. So with X-ray, one can detect where there is fault on the body of the patient, and proper treatment is being administered. If you consider or look at the figure we had for electromagnetic spectrum, you see that X-ray lies in between the gamma ray and the UV ray. Okay, so this region extends from 1 nanometer to 0.01 nanometer. It lies between the gamma ray and the UV ray. They are produced when fast-moving electrons are allowed to strike a heavy metallic target. The question now is, how can X-rays be produced? X-rays can be produced when fast-moving electrons are allowed to strike a heavy target. They are used as diagnostic tools in medicine and in scientific studies. They can damage living tissues and organs in the body. So this is not organization, but organs. Organs, okay. Alright, so let's consider the UV ray, the ultraviolet ray. Ultraviolet radiation region extends from 380 nanometer to 600 nanometer. And of course, this radiation lies between the X-ray and the visible light. I hope you remember. The sun is closest, the sun is the most important source of the ultraviolet radiation. So the sun is the source of the ultraviolet radiation. The UV radiation, the ultraviolet radiation, helps in introducing vitamin D and tanning to humans. So that's another benefit of the UV radiation. It introduces vitamin D, and also it gives us a specific skin color. That's what the word tanning is referring to. It gives us vitamin D and gives us a good skin color. However, a large dose of UV radiation can produce skin cancer in the body. So in as much as the UV radiation is helpful, it can as well lead to cancer if we are being exposed to excessive dose of it. So the ozone layer in the atmosphere absorbs most of the UV radiation from the sun. You can now see that the ozone layer is very important. So it's dangerous if our ozone tends to be depleted. Ozone depletion talks about the breaking down of the ozone layer. So if it breaks down, if it reduces in thickness, then the amount of UV radiation that will enter the Earth's surface or humans would be exposed to would tend to be dangerous to us. So the ozone protects against deadly radiation from the sun. When the ozone layer is depleted, it causes more of sunburn. The visible light. Visible light region of the spectrum ranges between 400 nanometer to 700 nanometer. So the range of the visible light is between the 400 nanometer to 700 nanometer. Our human eye can detect light at or electromagnetic wave at this region. Yes, between 400 nanometer to 700 nanometer. Visible light are produced when electrons in atoms and molecules undergo transition between energy levels. So one could say, how are visible light produced? They are produced when electrons in atoms and molecules undergo transition between energy levels. So when an electron gains energy and it now moves from one energy level to another energy level, radiation is being released. So that's how visible light are formed. The sensitivity of the human eye is a function of the wavelength of light. The sensitivity is maximum at about 560 nanometer, which is the wavelength of green to yellow light. If you could recall what they mean by dissipation of light, it talks about the separation of white light into different colors. Separation of white light into different colors. Let me draw a certain figure here. So assuming you have the prism, let's assume that light is being focused on this prism. You see that it will travel at different wavelengths. Okay, you have something like that. So you see light travel at different wavelengths and frequencies. So the separation of white light into different colors is referred to as dissipation. When light is separated into different colors, you have the following. Right. Beef. Okay. Right beef. So this one represents red color, orange color, yellow color, green color, blue color, indigo, and violet. Okay. So the last statement we had here said that the sensitivity of the human eye is a function of wavelength of light. The sensitivity is maximum at about 560 nanometer, which is the wavelength of green and yellow light. So the human eye is sensitive where you have the green and the yellow light. You have about 560 nanometer. Okay, so the term monochromatic light refers to light of a single wavelength or small band of wavelength. So that's just a term to note. When you have different colors of white light being separated to different frequencies, those are monochromatic light of a particular frequency. And the separation of white light into different colors is referred to as dissipation. You see that the wavelength that is closest to the region of the UV ray tends to be faster. So you have the violet at this region, and the region where you have 700 nanometer, you have the red color at that region. Looking at this table here would explain better. So here, this side is close to where you have the UV ray. It has a shorter wavelength, so it tends to be more faster. You have violet. After violet is blue color, then green, and yellow. So green has 560 nanometer at one point here, and then yellow light also has 560. And that statement said that at this point, our eye is most sensitive to light. Okay, we have the orange and then the red, the rainbow color. Okay, let me proceed. The infrared. Looking at this figure, if you could recall the era of COVID-19, you remember that this instrument was used. Most times you go to the bank, they have to first check your temperature by pointing it on your forehead. This is an infrared thermometer. It helps you to get information about the body temperature even without contact. This one is the remote control of that your television operates at the frequency of the infrared radiation. This is the television, this is the TV remote, and all of that. So that's an application of infrared. Let's look at other explanations. The infrared radiation starts from the longest wavelength of visible light. So when you have the longest wavelength of visible light, the shortest. What is the shortest wavelength of visible light? You have to think about that. I've already explained that. So this statement says infrared radiation starts from the longest wavelength of visible light, which is 700 nanometer to 1 millimeter. If you don't call it infrared radiation, you can call it heating effect or heat waves. So another name for infrared is heat. Our body emits infrared. Yes, our body as humans emits infrared. That's why if you stay in a place that is congested, you feel uncomfortable because of the amount of heat being emitted out of the body of people. Okay, let's move forward. It is produced by hot bodies and molecules. So infrared is produced by hot bodies and molecules. It has many applications to promote local blood circulation. It could be applied in the medical field. One of the applications is that it could be used to promote local blood circulation to reduce muscle tension, to relieve muscle pain, treatment of autoimmune disease, wound healing disorder. Infrared thermometers have mentioned that thermal imaging cameras for security. In this generation, presently, when you go to places, you see the CCTV camera. Most of those cameras operate at the frequency of infrared. So even at night, where there is no light, it has the ability to still record what is happening. Some of the animals, like cats and even the snakes, you see them, some animals that fly or even move at night they see at this frequency range. So a human being who jumps into a particular a certain compound with the intention of stealing, and suddenly you see a dog and you hide, you are not hiding because the dog sees you clearly. They have the ability to see even at the infrared region or range. So astronomy and meteorology for weather prediction, we can as well use this infrared for weather prediction, and as well could be applied in spectroscopy, the infrared radiation. the microwave. Can microwave pass through glass or plastic? This is a question. Can microwave penetrate glass or plastic? If we continue further, you will understand, you would even be the one to answer the question for yourself. But I still say yes. This is a figure representing a microwave oven, and you see mostly microwave oven, they use plastics and glasses to make them. Some of the cooker we use to prepare our food are applications of microwave. What instrument can be used to produce microwave? What instruments can be used to produce microwaves? Microwave can be produced by special vacuum tubes such as the klystron, magnetrons, and the gun diode. You can use the klystron, the magnetron, and the gun diodes to produce microwaves. What are microwaves? What are microwaves? Microwaves are electromagnetic radiations with frequency ranges between 300 MHz to 300 GHz. They fall between infrared and radio wave. Microwave have wavelengths that range from 1 mm to 15 cm. They are generated by oscillations of electrons in electronic devices. So one could say, how are microwaves, or how can we produce microwaves? How are microwaves generated? They can be generated by oscillations of electrons in electronic devices. Klystron is a device that can produce microwave up to 30 GHz and wavelength of 1 cm. They are used in radar. What is radar? Radio detection and ranging. They are used in radio detection and ranging. Please note that acronym. Note that acronym. What's the full meaning of radar? Radio detection and ranging. Okay, so what was I trying to say? Microwaves can be used in radio detection and ranging, could be used in communications, in mobile phones, transmitting of information, remote sensing, cooking, baking, and all of that. Microwave can penetrate glass and plastic. This was the first question that we asked. First question I asked, can microwave penetrate glass or plastic? Yes, microwave can penetrate glass and plastics. This is why plastic and glasses are used in microwave cooker and ovens, other than the use of metallic substances to avoid reflection. So this is the reason why they use glass and plastic, because they can penetrate through those ones, and metallic substances are being avoided to avoid reflection. Radio waves. The radio and television wave range from 15 cm to 2000 meter. They are generated by accelerating charges through conducting wire. I had to underline this because it is a sensitive point. One could ask, how are radio waves generated? They are generated by accelerating charges through conducting wires. They are used in radio and television telecommunication system. The AM broadcast at frequency range of 5.4 times 10 to the power 5 Hertz to 1.6 times 10 to the power 6 Hertz. And the FM radio broadcasts at frequency range of 8.8 times 10 to the power 7 Hertz to 1.08 times 10 to the power 8 Hertz. Please, you are watching Supreme Online Lectures. I would like you to subscribe to our channel and also introduce us to a friend if you are watching on YouTube. If you are watching on Facebook, it's still the same name, and you can also follow our page. Please, I would really appreciate. Let's take the last point before we end for the day. This one says properties of magnetic waves. Properties of magnetic waves. These are the properties of magnetic waves. If they say property, what does that mean? Okay, let's look at this. Even the wave has properties. They are transverse waves. So electromagnetic waves are transverse waves. Both the electric field and magnetic field are perpendicular, or they travel perpendicular to the direction of the wave. So they are transverse wave. The second point says that there is a definite ratio between the magnitude. You have this expression here, E equals to CB. So you have electric field, magnetic field, and then the speed of light is a constant. So this ratio can help us to determine the other parameter as well. Okay, so there is a definite ratio between the magnitudes of electric field and magnetic field. The next point says that the wave travel in a vacuum with a constant speed. So every electromagnetic wave travel at the speed of light. Electromagnetic wave require no medium of propagation. That's why the radiation from the sun, even when it travels through space, how does it get to the earth? It travels even through space because it is an electromagnetic wave, and electromagnetic wave do not require material medium for them to propagate. Doesn't need something to support its movement. It has the potential to travel even on its own. And lastly, they can be plane polarized. Electromagnetic waves can be plane polarized. What is polarization? When you have light that travels in all directions such that that light is made to travel only in one plane. When light is made to travel only in one plane, that light is said to be polarized. You can only polarize electromagnetic waves, and light is one of them. But other forms of wave, like the sound wave, cannot be polarized. Or plane polarized, I mean. Okay. Please, you're watching Supreme Online Lectures. I really thank you for your time. I appreciate you for watching. Please do us a favor. If you have already subscribed to our channel, thank you so much. If you are yet to subscribe, please do so. Do so now, please. I am begging. Thank you very much. I will love to see you in our next class. Have a wonderful day. Bye.